Okay, like I said, this is going to be the lab lecture for the iodine lab, because the iodine lab it's our last lab. Hey, is everybody happy with that? I'm happy. And so you've got your revisions that you'll make on the carbon monoxide lab, but that's really on you. We're not going to meet that week. You'll just have that week to work on the revisions, and you'll turn everything in to the TA or to the Blackboard. But this week, this is the sort of pinnacle lab that we do. Is the Ro-Vibr-Onic. So we have rotational, vibrational, and electronic transitions happening at the same time. So this is the most complicated spectral transition that we will experience in our lab, experience. So we're going to go through all of the different changes for rotation, vibration, and electronic. And the thing is, we won't resolve the rotational work, rotational lines, because we just don't have a high resolution enough spectrometer. You can resolve these Ro-Vibr-Onic transitions if you have a super high resolution laser, and we were able to do that in my graduate work. We had a really good laser lab, and we could resolve the emission lines for the iodine. It was pretty cool. Can I get you to close that door? So this is what we're doing. We're doing a diatomic electronic transition. And so the vibrational transitions are only resolved in the gas phase and for very small molecules. Think about this, though. You have 3n-6 vibrations. Does everybody remember that? We went through that all the time. You have three translations, 2 or 3 rotations, depending on if the molecule is linear. If it's linear, you only have 2 rotations. And then whatever's left after that, you have 3n total motions of a molecule, 3 times the number of atoms. You subtract out the 3 translations. And for iodine, you subtract out 2 of the rotations, and the only motion left is a vibration, and we only have 1 vibration in a diatomic molecule. So that makes things very simple. So if it's more than a diatomic, you have 3n-6 vibrations, and the signals are all overlapped. And so you end up with just the absorption that looks like the Jablonski diagram. You have all these vibrational levels, and you don't resolve any of them. So iodine is somewhat unique in that it's a big enough molecule. It's got a floppy electron cloud. Its absorption is in the visible range, and so it's a colored molecule. You see a purple gas when you warm up iodine. The gas is purple. It's absorbing quite a bit of the blue and leaving behind a little bit of the blue light and the red, and so you get a purple color. And so we're able to resolve these vibrational transitions. The rotational transitions are almost never resolved without a high resolution laser. So we're going from the ground state up to this excited electronic state, and then we're also going from the ground vibrational wave functions to the excited vibrational wave functions. And so we have this sort of, we talked about when we were talking about the atoms and the electrons, the nuclei. This was very similar to the Born-Oppenheimer approximation. So we said that the electrons can move really quickly, way faster than the atoms. And so we have vertical transitions in these electronic transitions. So this vertical transition means that this line right here is vertical on this internuclear distance. Because the speed of light comes in, the rapidity of the electron cloud being able to absorb that light, the atoms don't have any time to move further apart or closer together. So it's like a snapshot. Light comes in, it's absorbed, the atoms haven't moved at all. And so we go from this ground electronic state, which has an equilibrium bond length right here. So that's the bond length of the ground state. It jumps up here, and now it's way up the wall of its potential energy surface, and this is the bond length of the excited state. And that makes sense. A lot of times, I mean, what determines the bond length, the minimum of this potential, is the electron cloud. If we excite the electron cloud, now we have a different potential. So we might have a different bond length, and many times we do. Sometimes the bond length is shorter, but most of the time it's longer. So these intensities are called the Frank-Condon factors, and it's a simplified version of our transition dipole moment integral. It doesn't have x in the middle. It just has the lower state wave function and the upper state wave function. And so we see this Frank-Condon factor principle here in these intensities. Let me show you this. The shape of this ground state vibrational wave function is a Gaussian, right? It looks like this. you know what a Gaussian looks like. And it overlaps with these, I don't know, 7 or 8, it looks like 6 different wave functions. So if we were to take this function here, you know, the maximum is going to hit somewhere around the 4th one. You know, 1, 2, 3, 4. It's going to hit this one. That's the maximum, because it's right above the top of this Gaussian. And then it goes down either side. And so what we see in the absorption spectrum, you see this shape right here? That's the shape of the ground state wave function. So you got that Gaussian shape, and some particular molecules, you know, this is oscillating back and forth. This is internuclear distance. And so in our little sample of molecules, some of them are compressed when light hits them. And so then that part of the wave function is overlapped with the wave function up above. But it's not a lot of those molecules. Most of the molecules are near the equilibrium bond length, but some molecules are compressed when light comes in. Some molecules are stretched when light comes in. And so we have this shape that's distributed across the ground electronic state, superimposed on the excited electronic state. And so that's why we get this shape. Now, what about these widths here? These widths right here are related to the uncertainty in this vibrational energy level. So what could make this vibrational energy level uncertain up or down? Well, this molecule could also be experiencing external factors. Maybe it's in the middle of a collision when light hits it, and so it's got some perturbed outside force, and that broadens the energy levels just ever so slightly. But not all the molecules are in the midst of a collision. Most of them are in their unperturbed state, but you have collisional broadening. That's one of the things that you can see. And so that's something that causes these individual absorptions to be broad. So you could have collisions. What else could you have? Well, you could have the molecule coming towards the source. So some of the molecules are headed towards the source, and they experience a little bit shorter wavelength because they're coming at the light. Other molecules are moving away from the source, so they experience a little bit longer wavelength. That's going to make the energy levels appear closer or farther apart. And so you could have collisions, you could have Doppler broadening is what we call that. The Doppler effect, which is the velocity of the molecule coming towards or away from the source. And it's the same kind of thing as a train whistle. You hear a train coming by. When it's coming towards you, the pitch is going higher and higher. As it passes, it gets lower and lower. So molecules coming towards the source are experiencing a higher frequency light, and molecules going away are experiencing a lower frequency light. And that can cause those peaks to broaden. And then you also have just the spectral resolution spectrometer. And we can really see that spectrometer resolution here. At a really low resolution spectrometer, you don't resolve those peaks. And at a high resolution spectrometer, you can resolve those peaks. So in our particular spectrum, years ago, I wanted to give you guys more time to analyze the data, but the sacrifice of that is you don't get to sit up in the shared instrument space for 30 minutes while this collects the data. So we would put the iodine cell in the UV-Vis spectrometer. We would crank the resolution down as far as possible, so the slits were very narrow. We're scanning the monochromator as slow as possible, and it would take about 30, 35, 40 minutes to collect this spectrum. So I've saved you that amount of time in the 4-hour lab to continue to work on the data. But it is something that, I mean, I think this experience is somewhat valuable, so let's just pretend that we sat there for 30 minutes. Well, this spectrum came out very slowly, and you see the peaks bounce along. And that's somewhat exciting, but after a while you're like, okay, can we go down to the lab? Yeah, so that's what we do. Okay, now let's talk about the line shape. These peaks right here, these individual peaks here are very symmetric. Let's see. So this peak right here, individual transitions may be very symmetric. So But when you have all of those peaks with varying intensity summed up underneath a larger peak, then you can get asymmetric peaks. And so that's what we're going to be talking about next. So down here in the lower state, so this is our transition dipole moment integral. We're talking about the intensity factor. Down here, what are the different things you have for your molecule? Well, it's in the ground electronic state, so that's indicated by X. So that's the electronic state. It's really not a quantum number, but it serves the same purpose. It's a designation for that ground state. Kind of like in the atoms, we started naming things with term symbols and so on. The concept of quantum number is still there, but it's not as simple as like we had for the J values, right? You had J values 0, 1, 2, 3. Those were individual quantum numbers or vibrational quantum numbers. We get into electronic states, it's still quantum numbers. We're just using letters to describe them. And X is always the ground one. So we pick the ground, whatever the ground electronic state, we call that X. Okay. And then we have the vibrational level. V double prime equals 0 for this one here. But we're also in the iodine lab going to have V double prime equals 1 and 2. So we're going to have 3 lower vibrational states. So we have down here 0, 1, and 2. And then the J values, we're going to have a whole bunch of J values, and you'll see that on this chart. And then up here, we have the A state. And then, like if we were to go even higher, we'd have B, C, D. So we're just labeling these electronic excitations in alphabetical order. But X is the ground state, and then it starts with A and B and C and so on. It goes up. And then up there, we're hitting, say in this case, the V prime equals 4 level, and we have the J values. So let's look at those J values. In the carbon monoxide lab, we really only had one rotational constant, because we were in the ground electronic state, and it had one vibration, it had one bond length and one reduced mass, right? When we go to an excited state, we don't change the reduced mass, but look at the bond length. The bond length is different. So we have a different rotational constant in the excited state. Now, aren't you glad that we're not doing the rotational levels? Because our P, Q, and R branches would have different B values. And that would be kind of a mess. And it's fun to do that lab, but we're okay. This will be our last one. Okay. But what you end up having is, look at the energy spacing here. These are the rotational energy levels. And this is what you had for the carbon monoxide lab. And you were just going from V equals 0 to V equals 1. So these levels were the same spacing in 0 and 1. Technically, they were slightly different, but not so you'd notice. Okay. So, but they were almost the same. But look up here, we have a dramatically different spacing in the excited electronic state because we have a dramatically different bond length. So what that means is our rotational lines, what I've drawn here with these rotational lines is I'm showing that if we were to plot the spectrum down here, each of these little peaks, so if this is, let's see, how is this written? We'll say this is wave, high wave number, yeah. And this is low wave number, because the P branch is on the low wave number side, right? So notice how the blue lines, I'm just drawing the stick spectrum, they stop here and they wrap back around on each other and they start going to low wave number values. And then the P values go to low wave number values. So there's sort of a maximum on the R branch side where the absorptions stop. And that's called a band head. So if we were to plot this out at wavelength, we would see underneath all of this, we might have the center of the vibrational difference. So this would be nu 0 to nu 4. And then under here are the R branches, and the R branches go up like that, and then they tail down to long wavelengths. And then the P branches are here, and they tail down. So notice that the peak maximum doesn't line up with nu 0 difference. And the position of this band head is actually what we want to label. So we're going to pick this spot right here. This is the main point of the lab. If in the peak picking, we're not going to pick the maximum of these peaks. They've analyzed this both ways, and so I'm just saving you the problem of doing the lab twice and seeing which one's more accurate. So in the past, they would do this lab twice, pick the peak maxima, come up with your constants, and then pick the minimum on the short wavelength side. Okay, so what we're going to do is we're going to pick the minimum on the short wavelength side right here where this black arrow is. And we're going to analyze those positions, and we're going to get more accurate data. Okay. So we'll have more on that in a minute, but I just wanted to show you why we're picking that. It's because we're not resolving the rotational lines. We have these band heads, and that's a more accurate and more objectively easy point to pick than the peak maximum. Okay, so this is the I2 potential energy diagram. So this is the one out of the lab handout, and it's got all of the data, all of the parameters that we're going to analyze. So we have the electronic states, and we're actually, there's an electronic state that's an A state in here somewhere. This is A, and we're not analyzing A. So we're jumping all the way to B. So we're going from the X to B transition. That's the electronic transition. And then we're going from the 0 double prime to several states in the excited state, from 1 double prime to several states, and from 2 double prime to several states. Now, why can't we just do 0? Why do we have to do 1 and 2? Well, because this is a molecule that's pretty big, and its vibrational frequency is only 200 wave numbers, 214. And so at room temperature, we have excited molecules vibrationally. So we have some iodine molecules that are thermally excited into the first vibrational state and thermally excited into the second. And so nature is giving us all three. And so we're just going to analyze the data as it is. It's very hard to just pick out the zeros, but we could do that, but we're going to pick out the zeros, and by doing so, we'll identify the ones and the twos. So these are the vibrational levels that we will analyze. We're also going to get these equilibrium bond lengths here. And we're going to get this electronic energy difference. So the difference between the minima of these two potential energy surfaces, that's the new electronic. So that's the difference in electronic energy, potential energy surfaces. The bond energies, so the bond dissociation energies, how strong the upper state bond is. Look how much weaker it is. See, that arrow is really small compared to this one. So the excited state is excited, and it has a weaker bond. So it has a longer bond length. And then this difference between the dissociated atoms is the atomic excitation energy. So notice the only difference between those two is this atom here. So this is an excited iodine. And you actually will pull this excitation energy from that lab handout. But we could have gotten that energy from the atomic spectral database, the Grotrian diagrams. We could figure out, what energy level that is that the B state dissociates to, and we could pull that out of the spectral database. So this absorption of iodine, if we take this plot and turn it sideways, we can see here kind of our spectrum. We've got a bunch of little peaks in our spectrum, and they all correspond to different vibrational transitions on top of the electronic transition. So everything in the visible spectrum is an electronic transition, and we're resolving individual vibrational jumps. So here's a picture of two of those peaks. In this particular case, they both start in the V double prime equals 0. And this one's going to 14 right here. And you see the different length of arrow, right? And this one is going to 15. So whenever we do the assignment, this is what we're assigning. We're assigning these quantum numbers to every one of the peaks. So that's your job first, is to go through the spectrum and identify and peak pick and assign the lower state V value and the upper state V. And once you get up the tables of all of those, then you'll be able to do a regression and pull out all of the physical constants. And so some of the terminology used in this lab, this again is the most complicated energy transition that we have. So the frequency that we measure in the spectrometer, so our measurement, has an electronic energy difference, it has a vibrational energy difference, and a rotational energy difference. Now, I mean, I didn't want to use E for all of these, and in fact, the Nibbler handout, the textbook handout, is using this terminology. So they're using T for the electronic, G for the vibrational, and F for the rotational. And how do I know that? Well, look at this is the rotational quantum number, J. We're familiar with that. This is the vibrational quantum number, V. And then T, electronic, that's just given to us. So we cannot resolve the rotational lines. And so this is simplified. We're not gonna calculate that difference. And so then in this part is just this new electronic. And so this is the piece right here that we're going to analyze. So we know the vibrational energy equation, G of V. It's the vibrational frequency here times the vibrational quantum number plus a half. So this is what we were looking at in, say, the benzene, chlorobenzene lab. We were looking at the fundamentals going from V equals 0 to V equals 1. But in this lab for iodine, we're studying so many energy levels that we're actually going to be able to determine the anharmonicity constant. So this piece is the anharmonicity. So we will actually be able to determine how anharmonic this molecule is, right? And so those energy levels get closer together as the molecule gets excited, and you'll be able to determine that. So we would go through and we would identify all of our peaks. So we make a table, we measure these things right here. So we pick these. So this, and then that each transition is a function of the electronic difference, the vibrational quantum number in the upper state, the vibrational quantum number in the lower state. So we see this right here. We take G of V prime and subtract GV double prime. So this is the V prime ones. So we have a plus value here and a minus value here. You see this minus sign here. And then when we subtract the V double primes, we get a minus sign here and minus a minus. So it becomes positive. So that's why that's a positive. When we peak this is our spectral peak pick values. So I'll just write this peak, picked frequencies. In wave numbers. And then we assign the quantum numbers. So we assign V prime and V double primes. So this is what we mean by spectral assignment. For every peak picked value, we give it the quantum numbers. Just like you did for the J values. For every R and P line, you said this is J. If it's a P1, it's a J double prime 1 to J prime 0. And if it's an R5, it's a 5 to 6. And you assign all of those. You assign the upper quantum number and the lower quantum number. And when you get that table built, then you can do a regression analysis. So we make our columns, the V prime plus a half column, okay? And then you make a V prime plus a half column squared, okay? So you have that same value, but you have it squared. And then you have what I would do is I would make a minus V double prime plus a half column and a V double prime plus a half squared column. So for the negative ones right here, I would go ahead and make that column a negative V prime plus a half squared, so that the negative sign is built into the column. And then when you get your ANOVA table, your coefficient is positive. Okay. It's not critical that you do that as long as you recognize that whatever's in front of this column is what you're going to get in the ANOVA table. And so if you didn't put the negative sign in the column, then your coefficient's going to come out negative. And so and you compare it to literature, all your literature values are going to be positive, right? So just push this negative over here, make a column of minus V double prime plus a half. And then when you do the regression on it, the coefficient for column 3 will be this vibrational frequency in the lower state, the lower electronic state. So now let's figure out how to assign this spectrum. So here's the spectrum that you're going to get. And like I said, it took about 30 minutes to get. You scan the spectrometer very slowly, and so if we were sitting up there in the lab on the floor, it would just be going about this fast. It just take forever. And you just see the screen, and you see this little plot out. And we used to get these on chart paper. It would just come out and it would be chart paper, and you'd use your ruler to measure. If you had something in between the little blocks on the chart paper, you would interpolate and come down and find out what wavelength you were at. And so we had this long 8-foot table, and everybody working on different parts of it. And yeah, our spectrum would be that long, like 8 to 10 feet long. So I love the digital age. It's great. So you can do the same kind of thing. So what we're going to do is we're going to analyze every one of these peaks. So these little bumps are real. These bumps are the vibrational transitions on top of an electronic transition. And so this is a lot of peaks to assign, but you can do it. You've done worse. Okay. So let's see how this it looks like a wavy pattern, and it looks like two waves are mixing right here. You see that? The kind of confused area, that's the key spot that you want to zoom in on. So when we zoom in on that spot, then we get this. And this particular slide in your notes is the key to this lab. So we have the 3 series here. All of these peaks that are connected by these orange lines have the lower state V value equals 0. Then the blue lines originate in V double prime equals 1, and then the red lines, or brick colored brick red lines, look like or come from V double prime equals 2. And then the vertical lines that I've drawn on here are the upper state quantum numbers. And so let's just this little pattern right here is the one you're looking for. So if you're looking at the peaks, you see it does this pattern: high, low, about the same, low, high. So that's where they crash into each other. That's the spot you're going to start your peak picking at. And so also notice we're not picking the peak maxima, we're picking the minimum on the short wavelength side. So right there in the middle of that pattern where you have two peaks that are almost exactly the same size, for this particular peak, the minimum on the short wavelength side is this blue line right here. And so let's use my key to figure that out. What should I put as the upper state quantum number for this blue line? So I'm labeling every 5 ones here. So this one is 20, and it's going towards 25. So this one's 21, and this one's 22. Okay, so I would go and I would peak pick this. I would put that frequency in my table, and then in the V double prime column, I would write 1, and in the V prime column, I'd write 22. And then I would go to the next peak and pick the next one. So this next one up here is in a different series. Its quantum labels would be V double prime equals 0 and V prime equals 20. And it just happens that those arrows going from the 0 state to 22 and going from the 1 state to 22 and the 0 state to 20, those arrows are almost the same length. And so they show up right next to each other in the spectrum. Okay. So this is how you will put all this together. So you'll go and you'll take the data down from Blackboard, import it into Excel, and create a scatter chart of your spectrum. And then you can double click the x-axis and expand it and hover the mouse over to find the band head position, and then you will put that in your table. So let's go through all of these steps. So you import the data into Excel. Okay, see, a lot of times when you bring in a text file of data, it is all dumped into one column. And so in most cases, you'll have to do this. You need to split it into the text to columns wizard. Have y'all had to do this in any of the labs before? This last one? Okay, so you're pros at this. But so we have this. Again, my little shortcuts, you click on the top column, Control-Shift-Down will select the whole thing. It'll go all the way to the bottom. And then you can click the Data tab or Data ribbon and do Text to Columns. And you want to pick Delimited. This is a tab delimited file. And so this is tab delimited. What was the one y'all did this past week? Was it comma or tab? Do you remember? Yeah. It's not really important. But if it's comma space or comma separated values, then you would click comma here. Sometimes it's space separated values. So this is, again, what it's saying is there something in this text file that allows me to split the data into columns? Okay. I do this a lot of times when I have a list of emails and I want to pull just the username out and throw away the shsu.edu. Okay. What would I split that on? I split it on the @ sign, right? Every email has an @ sign. And so I could come in here and I could put in other right here, click that and put an @ symbol there, and it would split it into two columns, and I could throw away the shsu.edu column. Okay. So this is what happens then. It uses that delimiter to split the columns, and so you can scroll up and down and see what it looks like and make sure everything is all clean, that you have wavelength on one column and the intensity on the other. So now we got our column and our data into two columns. Okay. And then we want to do the XY scatter chart. You've done a lot of these, but I wanted to sort of emphasize this in this lab here. Use this one for spectra because the markers get in the way. It looks like you drew the spectrum with a crayon. Okay. And then you never want to use these smooth lines, okay, because it adds wiggles and all kinds of things that are not real. In fact, I would never use a smooth line. If you're going to plot anything, especially if you're making a presentation or reporting data, if you have a chart and you draw a line on it, you better know the equation for that line, because you're making a claim. You're saying that there's an infinite number of data points. Between each two x points, there should be a y point. And if you don't know the equation for that line, you can't justify putting it on the chart. If you've got the smooth data, it's adding all kinds of waviness to those lines, and you don't know what the equation is. Now, am I breaking my rule by using this one? No, because it's drawing a straight line between every two data points. And so if you give me two data points, I can calculate what the line equation is, and I can tell you what every data point is in between those. If you were to twist my arm and say, tell me what's at this point right here, I was like, well, okay, give me some time. I could figure it out. But not with the smooth stuff. So forget about that. Don't do it. Use this one for small data sets and this one for small data sets. Okay. So here's our Excel graph. And you can double click on the x-axis and zoom in. So change that x-axis, really zoom in close. And so then you get this right here. See, I've got 555 to 565, and that's that region. And so this is the one I'm going to start with. I'm going to pick that minimum on the short wavelength side. So this peak is the one I'm labeling right here, and I'm picking the minimum on the short wavelength side, and it's 559.5 nanometers. And that happens to be coming from V double prime equals 1, and it's going to V prime equals 22. And this next one was 0, V double prime equals 0, going to V prime equals 20, I believe it was. It was on the previous slide. And so then this next one here is V double prime equals 1, V prime equals 23, because they get higher and higher as you go to short wavelength sides. So you just go through and you pick all of those and make your table. Okay, this is the last lab you have to do that in. Yay! So every once in a while, I hear some people grumble about peak picking. They're like, "Oh my gosh, peak picking!" Yeah, but it's what spectroscopists do. Okay, so hover the mouse, and that's essentially what I told you. Use that guide to start making your assignments. Okay, it does get a little bit. Let me go back and look at the 3 series. Come on. Yeah, right here. Okay. If you're not exactly confident in these over here, I get it. Okay, just go with my key. And my key's using the same data that you have, right? So just do your best to repeat this. This V double prime equals 2 series is coming in, strong peak, and then this is a very weak transition from the blue right here, and so most of this peak is the 2 to 17 transition, but there's a very little weak 1 to 15 on there, and so there's a little wiggle right there. So that's the red one, and there's a little wiggle right there. It really doesn't become a minimum. It's sort of an inflection point that you're looking for, and so these right here are the hardest ones to do. This one, this one, this one, this one, this one. So they're accurate, but I could understand if you're looking at that going, I don't believe you. Right? So I would say just do these. Follow the key and try to find them and pick the best point that you think you're picking, according to this key. But once you get to 20, you're really not going to be able to get it. Now, and here we have all 3 series kind of on top of each other. So these 3 right here, the orange one's easy to do, but the blue and the red are kind of fishy. Or what do I want to say? By faith in DW's key. Yeah. And if you wanted to say, well, I don't believe in DW's key and not include those, just those 3, the blue and the reds, we can see what happens to the lab, but you would have to justify that in your procedure and say, I wanted to see how far off my values were if I didn't include them, and who knows, maybe they get better. I don't know. But that'd be for the advanced student that wants to write a little bit more in their lab report. Okay. Okay, so then we make this assignment table. So we have the wavelength here, and when we use the formulas to convert that over to wave number, because we're going to analyze wave numbers. We've assigned the quantum numbers V double prime and V prime, and then we make those columns for the regression. So this is not the regression table. The regression table has the V plus a half, and then minus V plus a half squared for the upper state, and then the minus V plus a half and the plus V plus a half squared for the upper for the lower state. And then you can make a Deslanders table. This is required for the lab, and it's good for checking your quantum number assignments. So it's a kind of a tough table to make, because it's not easy to just copy your formulas down, because it's alternating formulas. So what we have across the top are the V double prime quantum numbers. So this is the V double prime 0, 1, and 2. And then going down the side, the rows are the V prime quantum numbers. And this is useful because we hit, say we hit level 14 from all 3. So we have the 0 to 14 transition here. We have the 1 to 14 transition here. And then we have the 2 to 14 transition here. So if I were to take the difference between those 3 peaks, those 3 transitions, I get a measurement for the ground vibrational state, right? So these are the vibrational differences between 0 and 1 and 0 and 1 and 2, because they all 3 have the same upper state. So the only difference between those arrows is the ground states. And that's kind of neat. We can see the difference between the the ground state vibrations. And so if we were to average these columns, we'd have the average vibrational state from 1 to 2. And if we were to average this column, we'd have the 0 to 1 vibrational state. But don't bother doing that because the regression is doing that for you. The regression is doing all of these averages behind the scenes, and you get the data out in the ANOVA, the analysis of variance. Now this difference is difference between 14 and 15, both originating from state 0. So notice this is 0 to 14 and 0 to 15, so this difference is the vibrational difference in the upper state. And notice that the ground vibrational difference is around 214, and the upper state is around 100. So that shows you that the vibrational levels in the excited electronic state are closer together than they are in the ground electronic state. And that's what we would expect. It's a weaker molecule, so it's easier to vibrate. So these are the results that you'll get from this iodine lab. You're going to have the ground vibrational frequency and the excited state vibrational frequency. You'll use those to calculate the force constants, and you'll propagate the uncertainty to get those force constants. You'll get the ground state anharmonicity constant and the excited state anharmonicity constant. And then you'll get these values here, which is these two multiplied by each other. So this one times this one is this, and that's actually in the literature. So when you do the literature comparison, you'll probably have to compare this to the literature, not this, because we won't have the XE written by itself typically. And you'll get this excitation energy, the new electronic. You'll also get an estimate of the ground dissociation energy and the upper state dissociation energy. And then you can compare all of these values. So yes, you did a lot of peak picking, but look at all the information you got about the iodine molecule. So this is this is sort of the highest art of spectroscopy. It's not just the forensic sort of I've got a carbonyl stretch in this molecule and I don't really know much more about it. This is the like squeezing a spectrum and wringing it out and getting every kind of physical information you can about a molecule out. So this is the height of spectroscopy, squeezing out every bit of physical information we can about a molecule, and you will have done that when you're done with this lab. So that's an achievement. And so everybody that goes through PChem, quantum, and spectroscopy, and no matter what university, is a very common lab. And so you get through this, you'll be able to have that shared experience with P chemists throughout time and space. So,